Okay, so I wanted to go over a couple last topics having to do with equilibrium. So the last thing that you might be asked to know about concerning how something affects an equilibrium constant or the position of an equilibrium reaction would be the addition of a catalyst. All right, so remember that catalysts are substances that can speed up a reaction. And the thing about adding a catalyst to an equilibrium reaction is that it would have no effect on the equilibrium position. All right. The only difference that you would have in a reaction that had a catalyst would be that it would eventually get to those equilibrium concentrations a little faster than there would be without the catalyst. All right. So if you consider this generic reaction, all right, so let's pretend that we start off where we have, all A and no B, all right. We know that it eventually will get to an equilibrium, and we can write the equilibrium constant like this right here, okay. Well, if we do it without a catalyst, all right, it will eventually get here, all right. If you measure the concentrations of B and A, you would get this ratio right here. The only thing about this ratio is it says nothing about how long it takes to get there. All right. If you were to do this in the presence of a catalyst, it would get to the exact same final endpoint. It's just it would get there a little bit faster. Okay, so the last topic that we want to cover concerning equilibrium constants is how they can be mathematically manipulated in different situations. All right, two of these we've already actually talked about before, and I'm just recapping those here. All right, the first is the relationship between the equilibrium constant if the reaction were to be written as the reverse reaction. All right. Remember that any given equilibrium constant has to be written for a specific shown reversible reaction. All right. For example, I could not say I could not define this particular equilibrium expression if I didn't also show this reaction right here. The issue is that since these are reversible reactions, there's no real reason that one has to be on the left and one has to be on the right. All right, I could just as easily write this reaction like this, where all I've done is switch the sides. All right, but since it can go either way, there's really no start or finish. It's just they can go back and forth between each other. All right, I use the example of, is ice the reactant and water the product? Or is water the reactant and ice the product? Well, it can go either way. All right. So if we define this one, if we define an equilibrium constant, and the parentheses F mean the forward reaction, all right, versus defining it for the reverse, and that's what this R means, you'd see that these are the two different expressions that you would get. All right, again, in both sides, all you're taking is the substance on the right side. That goes in the numerator. You take the substances on the left side. Those go in the denominator. Raise everything to the exponent, which corresponds to the coefficients that you see in these reactions. And one thing that you'll notice about these is that all that you're doing is switching what's in the numerator and what's in the denominator. All right, and there's a mathematical name for that. We call those things reciprocals. And so since the one of these guys is the reciprocal of the other, mathematically, we could write the following. All right, the KEQ of the forward written reaction is equal to 1 over the KEQ for the reverse reaction. All right, that's the definition of what a reciprocal is. Or actually, the reciprocal can either be defined as just flipping numerator and denominator, but for a constant, for a whole number, the reciprocal is just 1 over top of that. All right. So please be aware that this relationship exists, and that is definitely something that you're required to know for the IB curriculum. Okay, so the next one, again, is something that we've talked about before, and that is the where the equilibrium constant comes from. All right. So before I get into this, I do want to point out that it can be a little bit confusing because we use K to stand for constant in several different situations. Okay, so before going forward on this, I do want to point out one thing about the way that we write constants. All right, although it's kind of hard to tell the difference when I'm printing these, and I probably it's hard to distinguish between these, but like there's K's that refer to equilibrium constants, but we also dealt with K's when we were talking about rate constants. All right, and so I do want to point out that there is a difference in how they're written. K's, equilibrium constant K's tend to be capital K's, and when you're talking about rate constants, when we were talking about kinetics, those would be lowercase k's. All right, and so I apologize, I don't seem to be differentiating between that well, but remember when these are printed, there would be a difference. All right, so and I'm throwing that out there because we're going to be talking about both of those different types of constants with this. All right, so remember what equilibrium is. Equilibrium is whenever you get to the point where the forward rate of a reaction equals the reverse rate. All right, so if we have this reversible reaction right here, this K right here, Kf, would refer to the rate constant for the forward reaction of A going to B plus C. All right, Kr would be the reverse, or the rate constant for the reverse reaction, which is B plus C going to A. All right, remember these right here would be lowercase k's because they're referring to rate constants. All right, whereas the equilibrium constants up here would be an uppercase K. All right, so again, going back to kinetics, we could define the forward rate as whatever the reactants are times the rate constant. And remember that in order for this to be true, technically, this has to be an elementary reaction. All right, so we're going to assume that both the forward and the reverse here are elementary reactions. All right, so the reverse rate would be the opposite. All right, these are the two reactants in the reverse process multiplied by whatever that rate constant is right here. And we know that whenever you get to an equilibrium, the forward rate equals the reverse rate. So therefore, we could set these two things equal to each other. All right, so we would have this right here. All right, and that could be rearranged so that we get the constants on one side and we get the concentrations on the other, and you would get something like this. And hopefully you can notice that this expression right here is exactly what you would get if you were to write the equilibrium constant for this reversible reaction. All right, and so that is equal to KEQ. All right, so this is just a mathematical proof that all an equilibrium constant is, and again this should be capital K EQ, is the ratio between the forward rate constant and the reverse. Sorry, this should be an R right here. So you make sure that you correct that on yours. That should be capital like K with an R subscript right there. Okay, so the last mathematical relationship we want to talk about is what happens when you have an overall reaction, which is actually nothing but the two separate reactions done in sequence. All right, so if you have this equilibrium reaction, but then the product of that reaction can react with another reactant to have this equilibrium reaction, we actually have two reactions that are just done in sequence. All right, so if we had this equilibrium reaction, we could write this, we'll call this reaction number one. We would have this rate expression, and if we had this equilibrium reaction, we would have this rate reaction. All right, so even though this exists as as two separate reactions, we could come up with an overall reaction by adding these two reactions together. And again, the way that you do that is if you set them both up, if you have a product on one side which is exactly the same as a reactant on the other side, they would cancel each other out. All right, and then all you do is add up all the remaining reactants on both sides, and you add up all the remaining products on both sides. All right, so that's what this says right here. And if we did that for this reaction, here is what we would get. All right, notice that there is no C written in this expression right here, and that's because this C right here would cancel out with that C right there. All right, so if we wanted to write an equilibrium expression for the overall reaction, it would be done just the standard way. And what I want to show is that, notice one thing that's going to happen is that the overall constant, the overall equilibrium constant, is going to equal the product of the individual equilibrium constants. All right, so what do I mean by that? All right, well, we could take this rate constant right here, or sorry, not rate constant, equilibrium constant, and we can multiply it by this equilibrium constant, which would be right there. And if we did that, you'll notice that C, concentration of C here, would cancel with concentration of C right here, and we would be left with this expression right here. All right, notice that this expression that we got from multiplying these two things is the exact same thing as the overall rate constant if we were just to do that from scratch from this written reaction. All right, so that's a little mathematical proof that the equilibrium constant of the first reaction, that's what this is, times the equilibrium constant from the second reaction is going to equal the overall rate constant for this. All right, so this would be in the case where you have two sequential reactions. So far, I have not seen any practice problems that ask you to apply this. My understanding as of right now is that you're expected to understand this conceptually, but not necessarily apply this in practice problems. All right, if I do find practice problems where these are applied, I will certainly point them out. But as for right now, you would be expected to know that this relationship exists, but in terms of doing a specific reaction where it asks you to apply this, as for now, I'm not going to hold you responsible for that. All right, that's it for this video.